All right, students, Assalamu alaikum. Today we are doing AS Chemistry A levels, October number 2022, variant 2. All right, paper 2. Let's look at the first question. Species such as NH4 plus, ammonium, carbonate, PO4 3 minus are examples of molecular ions. They're also called polyatomic ions. All right. Ionic and covalent bonds both involve in electrostatic attraction between different species. Identify the species that are electrostatically attracted to one another. An ionic bond, a covalent bond. All right. So, so basically, over here we want to identify the species that are electrostatically attracted to one another. So, which one? So we can say that ammonium ion will be attracted to phosphate ion because of an ionic bond, because they are oppositely charged, or ammonium ion is going to be attracted to carbonate ion. That is also a that is also going to be a uh, ionic bond, right? So a cation, like in above situation, it is ammonium NH4 plus and anions, that is like in the above case CO3 minus 2. All right, a covalent bond. Now in the above situation, how can you identify the covalent bond? So the covalent bond would be between the atoms of the same ion, like the nitrogen and hydrogen, they are joined by covalent bonds. The carbon and oxygen, they are joined by covalent bond. The phosphorus and oxygen, they are joined by covalent bond. And why are they joined, or on what basis are they joined, or what is the covalent bond? It is the shared pair of electron between the two nuclei, right? Okay, so we write that it is the shared pair of electron and nuclei of two atoms. This is what pro, uh, produces a covalent bond. Like for example, the NH bond in ammonium, the NH bond in ammonium ion, NH4 positive ion. All right, so that is one way of answering this question. Moving on to the next question, complete table 1.1 to show the total numbers of proton and electrons in the molecular ions NH4 plus, CO3 2 minus, PO4 3 minus, and so on. All right, so in NH4 plus, how many electrons would there be? So because it means plus 1, so however many total number of protons it has, plus 1 would mean it has one less electron, right? So if it contains 7 protons because of nitrogen and 4 protons because of hydrogen, so it has 11 protons in total. It should have 10 electrons, right? Because that is why it has a plus 1 charge. Similarly, if it has 6 protons because of carbon, and each oxygen has how many? 8 protons. So 3 times 8 protons because of oxygen, so that would be 3 times 8 is 24. 24 plus 6 is 30. If it has 30 protons, then it must have 32 electrons because it has 2 more electrons, right? PO4 3 minus. Now phosphorus, um, its atomic number I believe was 15 if I'm not mistaken, but we can confirm it from over here. Phosphorus, yeah, its atomic number is 15. All right, so because phosphorus atomic number is 15, that means it contains 15 electrons, sorry, 15 protons, right? So phosphorus, it contains 15 protons, right? And then 4 oxygens contain 4 times 8 protons, that is 32. So what is 32 plus 15? It is 47. So this guy contains 47 protons, and because it has gained 3 electrons, it has a 3 minus charge, so it has 50 electrons. This is how you do it. Okay, NH4 plus is a Bronsted-Lowry acid. Define Bronsted-Lowry acid. All right, what are Bronsted-Lowry acids? So how could you define Bronsted-Lowry acids? Bronsted-Lowry acid would be an acid that is a proton donor, because Bronsted-Lowry, you have to use the word proton donor or proton acceptor. That is the basic thing. Acids are proton donors and bases are proton acceptors, right? So we will say that any species which has the capability, which has the ability to donate protons is Bronsted Lowry acid, full stop. Next, when NH4 plus aqueous is heated with NaOH aqueous, a pungent gas is produced. Write an ionic equation for this reaction. All right, so ammonium ion, when it reacts with sodium hydroxide, ammonia gas is produced. All right, so they want us to write the ionic equation for this reaction. The thing is, what is produced is ammonia. All right, what is actually produced over here is actually ammonia. All right, so to know what happens, basically ammonium ion is NH4 plus, right? And when it is in its aqueous state, it is actually NH4OH, right? And when it reacts with sodium hydroxide, it basically breaks into ammonia gas NH3, and it produces water, and sodium hydroxide remains in its place, right? This is what happens. This is the whole reaction. Now if you look at it, this whole thing is a spectator in this situation, right? In this scenario, NaOH is a spectator. So what is not a spectator? The ammonium hydroxide. Now because they have written ammonium aqueous separately, so we have to write this like this: NH4 plus and OH minus, like this. All right, and they are both aqueous, and this is a gas and this is a liquid. All right, states are changing, so we are writing the oxidation state on basis of change of state. So we will write NH4 plus aqueous plus OH minus aqueous gives NH3 gas plus H2O liquid. All right, this is the whole equation that you have to write. Okay, that pungent gas is basically ammonia, because whenever an alkali is added to an ammonium derivative compound, ammonium salt, ammonium hydroxide, ammonium solution, anything that contains NH4 plus, when you add a strong alkali, ammonia gas is produced. All right, next question. The nitrogen atom in NH4 plus is sp3 hybridized. Sp3 orbitals form from the mixing of 1 2s and 3 2p orbitals. All right, so sketch the shapes of 2s and 2px orbitals on the axis. So s is just this. All right, this is s, right? S doesn't really have any axis, it is on all axes because it is a single. Now 2px would mean the p orbital on the x-axis. Now you should know, and in the notes it is written, this is the x-axis p orbital, this is the y-axis p orbital, and this is the z-axis p orbital, right? Over here, this would be your x-axis orbital. If they had asked you for the y-axis orbital, you would have drawn this. If they had asked you for the z-axis orbital, you would have drawn this. Okay, so for now you're going to draw the x-axis orbital p like this. All right, next question. There are many naturally occurring hydrated compounds that contain anion phosphate. Name the anion phosphate. Wow, I have said it from my word. Okay, so it is phosphate, PHOSPHATE, and you have to mention the oxidation number of phosphorus, P. All right, so what would be the oxidation number of phosphorus over here? How would you know? You know that overall the four oxides, they have a charge of minus 8, right? They have a charge of minus 8. So what would be the charge on phosphorus, so that a total minus 3 charges left? Phosphorus must have a minus 5 charge, so that overall minus 3 charge remains, right? So phosphate has a plus 5 charge, therefore we write phosphate 5. Okay, next question. Struvite is a soft hydrated mineral with Mr245.3. The anhydrous form of mineral has the formula NH4MgPO4. Calculate the number of molecules of water of crystallization in struvite. Now the thing is, they've told us right now that struvite is NH4MgPO4 dot XH2O, and the mass of this guy is a total of 245.3, right? Okay, so if I know what is the mass of NH4 MgPO4, I can start working stuff out. So what would be the mass of NH4 MgPO4? For that we need to go to the periodic table, or when we go to the periodic table, right? We can look at the mass of nitrogen. Nitrogen is 14. Okay, what else? Whose else mass do we need? I think we needed the mass of magnesium. Magnesium is 24.3. Okay, and what else? Hydrogen. Hydrogen's mass is 1. Okay, and what else? Who else was required? I remember NH4 Mg, and I don't remember others, so let me just go look again. Okay, NH4 Mg, P and O4. All right, so we want to look at the mass of P, and we want to look at the mass of 4 as well, O as well. So O is 16 and P is 31 exactly. All right, so magnesium is 24.3, the rest are whole numbers, and we know which whole numbers they are. So let's just calculate the mass of NH4 MgPO4. All right, so this is 14.0 plus 4 plus 24.3 plus phosphorus is only 131.0, and oxygen is 4 times. The 4 times 16 is 64. I am not going slowly. 4 oxygens, 1 oxygen is 16, so 4 oxygen should be 4 times this, right? So when we add all the values together, 14 plus 4 plus 24 plus not 24, 24.3 plus 31 plus 64 equals to, so I am getting an answer of 137.3. 137.3. All right, so the mass of XH2O would be 245.3 minus 137.3. All right, so 245.3 minus our answer, we get 108. All right, so X is the value of how many moles of H2O, so we just have to divide it by the MR of H2O, right, which is 18. So it is 108 divided by 18. 108 when it is divided by 18 gives us exactly 6. So our answer over here is 6. I hope that makes sense. Okay. Next question then. Hydroxide OH negative aqueous reacts with 2-bromo-2-methyl propane in an SN1 reaction. The molecular ion CH3 whole thrice C plus forms as the intermediate in this reaction. Draw the mechanism of SN1 reaction. All right. So basically, hydroxide ion is reacting with 2-bromo-2-methyl propane. So 2-bromo-2-methyl propane is this CH3, C, CH3, CH3, and Br. This is 2-bromo-2-methylpropane. This guy is partially positive. This guy is partially negative. Uh, include charges, dipoles, everything, right? So yeah, we are going to include charges, dipoles, everything, as you can see. So Br will be partial negative. This guy will be partial positive. Okay. So we have a hydroxide ion that has an electron pair. This is a nucleophilic substitution reaction, as you know, right? The OH negative attacks. All right. And because it attacks, this bond is taken, right? So now we have the OH negative. It attacks the carbocation and it joins H3C, COH, CH3, CH3 like that, right? Okay, so we can draw that. Okay, I'm drawing OH twice, so it's better if I just draw it in the second one because the OH is not joined yet. In the first situation, we see that the bond is breaking and it's becoming partial positive and partial negative. All right. Next, 2-bromo-2-methylpropane is a tertiary bromoalkane. Define tertiary bromoalkane. So what would be a tertiary bromoalkane? A tertiary bromoalkane would be defined as a bromoalkane that has whose alpha carbon is joined to 3 other carbons. All right. So we will say the carbon, because the alpha carbon is not a concept that is in A levels, right? So we don't use the word alpha carbon. We will say the carbon bonded to bromine is joined with 3 other carbon atoms. फुल स्टॉप. ठीक है. Next question. Organic compound M forms when 2-bromo-2-methylpropane is heated with ethanolic OH negative. If the OH negative is not aqueous, if it is ethanolic, then an alkene forms, right? Then an alkene forms, as we know, right? So what would that alkene look like? So the alkene would be a double bond. Now that double bond could be between this carbon and this carbon, this carbon and this carbon, this carbon and this carbon, whichever carbon you want, all right? So all we have to do is draw the structure. So I like to do CH3 CH, no, there is no H, there is only a double bond. So make the double bond over here, make this CH2 then, and then this is CH3. This will be the structure. An alkene will be formed. This will be called 2-methyl prop 1-ene, right? The name of this compound would be 2-methyl prop 1-ene. Next question then. Question number two. Two chlorides of some of the period 3 element. The chlorides of the sum of the period 3 element are shown in table 2.1. Their bonding and structure is shown. Identify the covalent bonding shown by each chloride under standard conditions. Use C for covalent, I for ionic, and M for metallic. Identify the structure shown by each chloride under standard conditions. G for giant, S for simple. All right. So we have to identify a lot of things. Okay. So first of all, bonding for NaCl, it is ionic. Bonding for AlCl3, it is actually covalent. All right. AlCl3 is covalent. So is SiCl4 and so is PCl5. All right. Why did they not mention MgCl2? MgCl2 would have been ionic. All right. Next is structure. If they talk about structure, NaCl is a giant ionic compound. All right. Is a giant ionic compound. AlCl3 at this moment under standard conditions is giant, right? Al2Cl6 would have been simple. Okay. S, it would be simple. SiCl4 is going to be a simple covalent compound. It has a very low boiling point, and PCl5 also simple compound. All right. Oxidation state of period 3 element. Sodium over here has a +1 oxidation state. Aluminum over here has a +3 oxidation state. Silicon over here has a +4 oxidation state. Phosphorus has a +5 oxidation state. And then PCl3 also has a +3 oxidation state once again. And then SCl2, SCl2 would have oxidation state because it is into 2 chlorines. We had to just run through that. Next question, write equations for the reaction of NaCl and PCl5 with water. Well, NaCl, when it dissolves in H2O, it just basically just dissolves, right? It will not really completely do anything. It basically just becomes sodium ion aqueous. उसके बाद Cl minus aqueous. All right. Now we have PCl5. PCl5, when it mixes with water, this is a completely different case. This is not just dissolution. This is actually a chemical reaction, right? And the chemical reaction produces phosphoric acid, as we know, and it produces hydrogen chloride gas, right? It produces hydrogen chloride gas as well. Okay. Um, but hydrogen chloride gas, it would be soluble. Hydrogen chloride aqueous. All right. PO4, that is also an acid, that would be also aqueous. All right. H2O is liquid. All right. Next we have for this we can also write H plus OH minus aqueous. Everything ionizes when sodium chloride is dissolved. Okay. For this one, how do we balance it now? Because there are 5 Cl, we put a 5 over here. Because there are 4 oxygens, we put a 4 over here. Because now there are 4 twos are 8 hydrogens. So 3 plus 5, there are 8 hydrogens. Everything is balanced. So nothing to change more. Okay, that is it. Now let's move on to the next question. In the gas phase, AlCl3 exists at equilibrium with Al2Cl6. Draw the dot and cross diagram to complete the equation. All right, so we want to draw the dot and cross diagram. So let's just draw a circle of this size because this is the size I want all the chlorine atoms to be of. Okay, great. I want and another aluminum atom like this. Then we can duplicate two more chlorines like this, and now we have a total of how many chlorines? Way too many chlorines. This has to be deleted. Okay, so here's how it is. One second. This is how the structure is actually supposed to look like. Doesn't look as pretty as it is in the books, but this is more or less how supposedly it should look. In the text in the books, the aluminum chloride structure, it kind of has this resemblance, right? I think I had drawn it correctly. I have to duplicate another one. So now there are six chlorines. Yeah, yeah, like this. This is how the structure looks like: aluminum, chlorine, 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 and chlorine. All right. So both aluminums have three dot and crosses, three dots and three crosses. All right. So this guy also has three dots and three crosses, right? And then there are two dative bonds. So this is having a dative bond with this one, and this is having a dative bond with this one. This chlorine has a dot and cross diagram with this aluminum and a dative bond with this aluminum. And this chlorine has a dot and cross with this aluminum and a dative bond with this aluminum. This is how you draw it. Now, to fulfill the outer shell electrons, okay, because chlorines have been shown with a dot. So these are the crosses. Okay, one second. So because the cross is for aluminum, so dot is for chlorine over here. So we have to show dots for chlorines. Okay. So because each chlorine has given two electrons as dative bond, so it has four, and this one also has two lone pairs, meaning four electrons. And then this one has six electrons, meaning three lone pairs. That is all right. Now the next, state the effect of an increase in temperature on the equilibrium mixture in equation 1. Explain your answer. If we increase the temperature, the forward reaction, as you can see, is exothermic, and the backward reaction, as you can see, is endothermic, right? Increase in temperature shifts equilibrium in backward direction, right? So we will say position of equilibrium mixture will shift to left. Position of equilibrium will shift towards left. And why? As increase in temperature is favored by side with is favored by endothermic side. Let's call it endothermic side. Next question, beta. A 3.3 grams sample of a period 3 chloride is heated to 500 Kelvin in a sealed flask. At this temperature, the chloride is a gas of volume 250 centimeter cube and pressure in the flask is 323 kilopascals. Use the ideal gas equation to calculate MR of the period 3 chloride. Okay. So we know this, and we know that to calculate MR, we have a formula: moles is equals to mass upon MR. So if I want to calculate MR, we do mass upon N. For MR, we do mass upon N. Okay. Now, because for MR, we do mass upon N, because for MR, we will do mass upon N, right? So for that, we will now use the formula PV is equals to nRT. We already know the mass. It is 3.30. How do I know that? Because 3.30 sample has reacted, right? We just need to find the moles. We just need to find the moles. So we do N is equals to PV upon RT. N is equals to pressure. We change it to 323 into 10 to the power 3 pascals. Volume, we change it to 250 into 10 to the power minus 6 meter cube, right? Because we want the volume and pressure in meter cube and pascals. This is something you have to remember. Temperature is already given to us in Kelvin, so we'll keep the temperature in Kelvin. So now we put the equation in. Pressure is 323 into 10 to the power 3 multiply by 250 is the volume, multiply by 10 to the power minus 6 divided by R is 8.31. If you don't remember R, it is at the end of the paper, question paper, the constant values they are given to you, and multiply by 500. So how many moles would that be? Let me just calculate that out. 323 times 10 to the power 3 times 250 times 10 to the power minus 6 divided by 8.31 times 500 equals to, our answer is 0.019 moles. Our answer is 0.0194 moles actually. All right. So now we can calculate the MR. MR would be, MR is equals to mass upon moles. All right. The mass was 3.30 upon 0.0194. All right. So 3.30 upon 0.0194. We are getting an answer of 169.8. All right. So our answer is 169.8. Okay. Formula of period 3 chloride. If the MR is 169.8, then what could it be? Okay, so which chloride has a formula of 169.8? So we are going to have to find that out. Here are all the chlorides. Let's measure their masses. So NaCl is, I remember it is 58.5. So let's just leave that. Aluminum chloride, AlCl3. Aluminum beta is 27, you should remember. And 3 chlorines 27 plus 35.5 times 3, that is 133.5. So this is 133.5. Silicon, I don't remember the mass of silicon, so we go down here and check the mass of silicon. It is 28.1. Okay, so we'll come back up. Silicon is 28.1. 28.1 multiplied by 35.5 times 4, because 4 chlorines, right? Oh, sorry. 28.1 plus 35.5 times 4. The answer is 170.1. The answer is 170.1. So this is our period 3 chloride. So period 3 chloride must be SiCl4, because this answer is 169.8 and SiCl4 is 170.1, meaning a difference of 0.3, which is absolutely nothing. Next question. An excess of chloride Cl minus is added to 1 centimeter cube of bromine. Describe what is observed. There is no change. Why would there be no change if excess of chloride is added to 1 centimeter cube of bromine? Because chloride is the more reactive one, bromine is the less reactive one, right? So there is going to be no reaction over here. The bromine, because it is brown in color, will keep the solution brown. All right, so the solution will remain brown and no reaction will take place as bromine is less reactive and cannot displace chloride from its AQUE aqueous solution. Next question. SCl2 has MR 103.1 and is a liquid at room temperature. SBr2 has MR 191.9 and is a gas at room temperature. Explain the difference in physical state of SCl2 and SBr. Give your answer in terms of intermolecular forces. All right. So SCl2, it has an MR and it is liquid, and SBr2 has MR and it is a gas. Even though its MR is more, why is SCl2 a liquid and why is SBr a gas? The answer is very simple. The answer is very easy. Look, SCl2, because of the high difference in electronegativity, would have stronger intermolecular force of attraction. You can even use the words, say it has permanent dipole forces, whereas SBr2 would have induced dipole forces. All right. So we will say, when we say those two things, I think 2 marks are sufficient. That is sufficient knowledge for 2 marks. So we will talk about the intermolecular force. They have asked us for that. So we are going to say SCl2, as it has a higher difference of electronegativity, as it has a higher DIFFERENCE difference in electronegativity, will have a more polar bond. Stop. Hence, it will have stronger permanent dipole forces. While SBr2 has weaker instantaneous dipole, induced dipole forces of attraction. Full stop. Bismuth is a dense metal in the same group as phosphorus. Draw a label diagram to show the bonding in bismuth metal. All right, so we want to draw a label diagram to show the bonding in bismuth metal. How can we do that? How can we draw a label diagram to show bonding in bismuth metal? So we just draw the metallic bonding. All right, to draw the metallic bonding, all you need to do is do this and put a plus in the middle, and then go like this and duplicate it. All right, you want to draw 3 layers, so duplicate it one more time, and then you duplicate the 3 of them once, and then again. All right, now you might be thinking, sir, how could I do that in exam? Well, you'll have to manually draw them like this. All right, and then you draw this, and then you draw this, and you have drawn the bismuth metal, and now you have to draw delocalized electrons like this. All right, a sea of delocalized electrons, and the diagram must be labeled. As they have said, they want the label diagram, so we will say these are delocalized electrons. All right, and these are These are uniform layers, LAY, layers of positive metal ions. All right. So uniform layers of metal ions surrounded by sea of delocalized electrons. That is how you draw the delocalized electrons. Okay. Next question. Bismuth reacts with chlorine to form BiCl3. BiCl3 is solid at room temperature. It melts when heated gently. BiCl3 reacts vigorously with water at room temperature to form an acidic solution. Suggest the type of bonding and structure shown by BiCl3. Use your answer. So because BiCl3 is a very weak solid, right? It melts easily. So it should have a simple covalent compound, right? It should be a simple covalent compound with a simple molecular structure. Okay? So BiCl3 is a simple covalent compound with a simple molecular structure. All right. And they've asked us to explain our answers. Hence it has low melting point. They have told us that it has low melting point and forms acidic solution. Simple covalent compounds form acidic solutions. All right, as we have mentioned already, or as we have observed already. Okay. Next question, then, beta. Pretty huge question. It was of 21 marks. Now, on to the next question. Organic compounds can be distinguished using chemical tests and analytical techniques. Table 3.1 shows pairs of organic compounds. All right, this is a question. This is a similar question to what we had seen in a previous installment of this paper as well. Okay, so let's look at the questions then. Um, So the first we have to write down the reagent, and I think they'll tell us that use different reagents for each test. Yes, all right. So which reagent can distinguish between an aldehyde and a ketone? So which reagent can distinguish between an aldehyde and a ketone? So the only reagent that can completely distinguish between an aldehyde and a ketone is the Felling's test or the Tollens test, right? Because those are the ones that distinguish carbonyl compound, right? So we will say Felling's solution or Felling's reagent, all right, which is copper 2 oxide, basically CuO. Okay, so what will happen is copper 2 oxide will form copper 1 oxide. It will get reduced while aldehyde will oxidize. So we will say A1 will oxidize and cause formation of deep red precipitate, deep red or orange precipitate. All right, deep orange precipitate is formed from blue colored solution. Copper oxide is a blue colored solution. Felling reagent is a blue colored solution before. All right. Um, Next question. Uh, B1 and B2. Now B1 and B2 are both ketones, as you can see. This is a CH3 over here. This is not an aldehyde. All right. So they are both ketones, but this ketone has a CH2 CH3 on this side and a CH2 CH3 on this side, right? The carbonyl carbon is not joined with a CH3 group in B2, but in B1 it is. Only one test can distinguish this, and that is the alkaline iodine test, right? Alkaline I2. What do we see? If a CH3 is present, then the alkaline iodine will cause the formation of triiodomethane, which is a yellow colored precipitate, right? So we will say B1 will form a yellow colored precipitate. Full stop. Next question. Now the next question contains another ketone and it contains an ester, right? So this is a pure carbonyl carbon and this is not an impure carbonyl carbon. So we can use the 2,4 dinitrophenyl hydrazine, 2,4 DNPH. So yeah, so the name of DNPH is dinitrophenyl hydrazine. You should remember dinitrophenyl hydrazine. All right. And what do we see? We see that in C1 will produce orange, deep orange or orange colored precipitates, right? The dinitrophenyl hydrazine gives positive test for carbonyl carbons, which are aldehyde and ketones. Okay? So orange colored precipitate. Next question we have, we can see that this is an alcohol. This is also an alcohol, so we can't do a test for alcohol because both of them will give the positive result. But then we see this is a double bond and there is no double bond. This is a cyclo alcohol, contains completely saturated carbons. But this one contains an unsaturated carbon. So we can use aqueous bromine, AQUEOUS, aqueous bromine. So we can say in D2, color of will change from brown to colorless. That is what alkenes do. That is what alkenes do to bromine. All right. Next question. A1 and A2 are structural isomers. Define structural isomer. Compounds having same molecular formula. Compounds having same molecular formula but different structures. Full stop. Give the systemic name of B2. All right. So what is B2? B2 contains 5 carbons. 1, 2, 3, 4, 5, and the ketone is on the third carbon. So it will be called pentane 3,1. All right, it will be called pentane 3,1. Pentane 3,1. All right. Next, deduce the molecular formula of D1. D1's molecular formula. All right. So let's see. This carbon has all 4 bonds done. This carbon has 2 free bonds. This carbon has 2 free bonds. This carbon has 2 bonds. All right. So it becomes 1, 2, 3, 4, 5 carbons. C5. All right. How many hydrogens? 3 plus 2, 5, 6, 7, 8, 9. C5H9OH. This is the formula we have for our brother. Um, all right. So the formula is C5H9OH. So let's just write that down. Free marks C5H9OH. Next question. D2 forms polymer Z when heated gently. All right. So polymer Z is formed when D2 is heated gently. Identify the type of polymer that is formed from D2. So what is D2? D2 is this guy. All right. So D2 is an alkene. So the polymer that is formed from alkene is called an addition polymer. All right. So this is addition polymer. All right. Now D2 has, we have to draw the thing, right? So this is CH2 on this side and then CH, and this is 1 carbon and this is 2 carbon, H2, H2, right? So in total, we want to draw for polymer Z carbon carbon double bond. So one of the carbons is both hydrogens, as we can see, and 1 carbon has 1 hydrogen, and then it has 2 carbons, and on 2 carbons it has 4 hydrogens, and then it has OH, right? C2H4OH. That is something we can write for them, right? C2H4OH. All right, now we want to show the polymerization of this. So we've drawn the monomer like this, and then we can just polymerize it to polymerize it, there is only a single bond in the middle. Everything remains the same. H, 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 and C2, H4OH, and then you draw a long line this way, long line this way, and you put a bracket because you wanted to draw just one repeat unit, and then you put a N over here. All right, this is how you draw it. Next question. Organic compound E contains 3 carbon atoms. E reacts with cold dilute acidified KMnO4 to form a single compound F with MR 154.9. Figure 3.1 shows the infrared spectrum of E. Figure 3.2 shows the infrared spectrum of F. Okay, E reacts with cold dilute acidified KMnO4. That is very strange, right? Because cold dilute acidified KMnO4, where have we seen that? We've seen cold dilute acidified KMnO4 being used for alkenes, right? And when cold dilute acidified KMnO4 was used for alkenes, it used to produce alcohols. So a tentative guess is that E is an alkene, which means it is a carbon-carbon double bond, famous. And this is an alcohol, meaning OH bond should be over here, right? Alcohol and OH. This is our guess. And as we can see, we are 100% sure that F has alcohol, right? Because it has that huge fat peak over here that is of an alcohol, and E does not have that peak, meaning E was not an alcohol before. So meaning that whatever happened made E an alcohol. Now let's look at what the situation is going on. Bond, functional group, whatever. What are they asking us? Use the two infrared spectra in table 3.2 to identify the functional group present only in E. Explain your answer referring to only absorption frequencies of above 1500. So right away, I would try to go for C double bond C in alkene, and alkene are 1500 to 1680, right? So go to 1500 to 1680. We see that there is a peak. There is a peak right here. Circle it, put a carbon-carbon double bond so that if examiner is checking your paper, he sees that you have identified the carbon-carbon double bond. So E is an alkene, right? It contains the carbon-carbon double bond. And how do I know that? There is a sharp peak at wave number between 1500 to 1680. If we want to be exact, we can be exact as well. It is roughly at 1580, right? At approximately 1580. There is a sharp peak at approximately 1580 centimeter inverse. All right. Okay. Which is between 1560 to 1680, which is between 1500 to 1680. 1500 to 1680 centimeter inverse. Next, use the infrared spectrum F to identify functional group in E. So E has the functional group OH, alcohol. So we say it has the functional group alcohol. It has the OH functional group. All right. How do I know that it has the alcohol or hydroxy functional group? Because it contains a very fat peak. Well, we should not use the word fat. We should use the word OH, broad peak, right? The hydroxy peak. The hydroxy peak present between 3200 to 3650. So this is exactly where it is. If you look 3200 this, and on this side it's just above 3500 between 3600. So there is a very broad characteristic peak at 3200 to 3600 at in spectroscopy of F. Stop. Next question. The mass spectrum of E shows molecular ion peak and an M plus 2 peak of approximately equal abundance at M upon E equals 120 and 122. Reduce the relative molecular mass of E. All right. So they are saying that the molecular ion peak and the M plus 2 ion peak is of 120 and 122. Well, we know that E is an alkene, right? E is an alkene. So let's start writing alkenes down. C2H4, that is our first alkene. What is its mass? 28, right? So we know that each time when we add an alkene, each time when we add an alkene C3H6, the mass will increase by 14. If you don't believe that, just do this 3 times 12 plus 6 hydrogens. So that is 42. And just subtract 42 from 28. What do you see? You see that 14 is being added. So when we add 28 to 14, we get 42. We add another 14 to that, we get 56. Right? When we add another 14 after getting 56, we add another 14, we get 70. All right. After adding another 14, we get 84. After adding another 14, we get 98. So after adding another 14, we get 112. So now after adding another 14, we get 126. Oh, but we wanted to stop at 120. So we wanted to stop at 120. This question does not even ask us for the formula. This question asks us for the MR. Sorry, my bad. We were doing it wrong. This question doesn't ask for the molecular formula. This asks for the MR. Okay. So the thing is, to do the MR, first of all, we have to judge that the how the molecular ion peak and an M plus 2 peak is formed. Who creates the M plus 2 peak is a real question, right? Who creates the M plus 2 peak? That is a real question. For that, you have to see that the 120 and 122 mass are of equal abundance, 1:1, right? That is what is mentioned. And which isotope in our syllabus is an isotope that has a ratio of 1:1? All right. Which isotope has a ratio of 1:1? And in this question, it is not mentioned anywhere that anything that has a ratio of 1:1, but we know that the only two cases that we have studied, one is of chlorine, which has an M plus 2 peak, but it has a different ratio. It is a 3:1 ratio. And one is a bromine. When bromine we talk about, so one bromine mass is Br79 and one bromine mass is Br81, and they are in the ratio 1:1. So a Br79 could be over here giving us a 120 mass, and a Br81 could be over here giving us a 122 mass. All right. So the MR of the compound, the MR of the compound for now would be half of these two, right? Because it is 1:1. So what we will do is 122 plus 120 gives us, should be 121. All right. So the MR of the compound should be 121 because both the abundances are of the same ratio. So when we're trying to find out the MR, we take the average, right? The average is going to be taken like this because no matter which way you do it, if you said 50% and 50% and calculated it by putting 100 at the bottom and then using MR, relative molecular mass of one isotope multiplied by its abundance plus relative molecular mass of another isotope plus its abundance or so on. Okay. Now the next thing is use the information to suggest the structure of E. So I know I want to say that it contains a bromine. All right. And then it contains a carbon-carbon double bond as well. It contains a carbon-carbon double bond as well. All right. So this carbon should have one hydrogen to make the four bonds, and this carbon should have two bonds, right? One is a hydrogen. So this much is done. Now let's see how what is the mass. 12 plus 12 plus 79 plus 2, that is 105, right? So when we add another carbon and we add three hydrogens to it, so what will be the mass now? Three carbons, that is 3 times 12, 16, that is 36, plus 79, so that is 115. And how many hydrogens are there? One, two, three, four, five. Five hydrogens. Yeah. So this will be the molecular formula of our compound. How did I come to this? Because I know that if I use the 79 bromine, the overall mass should be 120. And if I use 81 bromine, the overall mass should be 122. Right? Without having bromine, this question can't be, because the M plus 1, the M peak and the M plus 2 peak are of equal abundances. That means it contains an atom that has two isotopes of equal abundance, and the only instance we have studied where two isotopes have equal abundance are these two. Okay, I hope that makes sense. Next question: complete the equation for the reactions of E with cold dilute acidified KMnO4 to form F in the equation. O represents cold dilute acidified KMnO4. So we want to complete the equation, so let's just complete the equation. C3H, or we can do it like this: CH3, CH2, not CH2, sorry, CH3, CH, CHBr. All right, and when they react, it forms a diol, right? So we say CH3, C, CHOH, or no, the H will just, the H will stay, the double bond breaks, yeah. The CHOH, another one. All right, and then Br. This will be our equation. And because we see that there are two O's over here, there are two O's over here, there are two hydrogens over here, there are two hydrogens over here. Everything seems to be completely balanced. Everything seems to be completely balanced. Next question. C2 can be synthesized using A1 as a single organic reactant. So we are saying that A1 can form C2. All right, how? First of all, we have to understand what C2 is. C2 is made up of a 3 carbon carboxylic acid and a 3 carbon alcohol, and A1 is a 3 carbon aldehyde. Okay, devise a multi-synthetic route to form C2 from A1. How can we make C2 from A1? So if you see C2, C2 can be broken down, I mean hydrolyzed into a carboxylic acid, which would be this one: CH3, CH2, COOH, right? And it is going to be reacted with CH3, CH2, CH2, OH, and alcohol. All right. Now this is propanol, and this is propanoic acid. And if you look at this one, this is propanol. Now propanol can be reduced to make propanol and oxidized to make propanoic acid. This is what we have to do. We have to take two samples of A1. One we have to reduce, one we have to oxidize. All right. So if we oxidize it, it becomes propanoic acid, and if we reduce it, it becomes propanol. All right. So we say take two portions. You take two portions of and refer to it as A1, not propanol. A1, full stop. To the first portion, add acidified aqueous KMnO4 to produce propanoic acid. All right. So you want to add acidified KMnO4 to produce propanoic acid. Now to the second portion, add Na, is it? No, LiAlH4. That is a better one. Li lithium aluminum hydride LiAlH4, add lithium aluminum hydride and warm the mixture to produce propanol. Full stop. Now react the two obtained mixtures with one another in presence of H2SO4 as catalyst to produce C2. All right, so you want to produce C2 this way. I hope that makes sense. And with that, this past paper has been completed. Another yet very easy simplified past paper. I hope you guys understood. If you have any questions, please do let me know.